I'm afraid grazie is the extent of my Italian. But we're going to start with a little magical story, because that's how my career actually began. This was when I was about 12 years old, and I was invited to a birthday party. And my friend's parents had hired a magician to entertain us. He wasn't very good. Most of the tricks he did I have long forgotten. But there was one that was life-changing. I want to share it with you. He showed us a rope. And of course, ropes are very flexible. But then he said he had a magic chemical in his pocket. So he took that magic invisible chemical, and he said that this could do wondrous things. It could make that rope defy gravity. We didn't know what he was talking about, but he sprinkled that chemical on the rope. And believe it or not, the rope defied gravity. I didn't know how he did that. I knew that if I tried to do it, it wouldn't work. But with his magic chemical, he was able to do that. I can only do that to ropes. Anyway, he said magic chemical. I didn't know anything about magic. I didn't know anything about chemistry. But I went to the school library, and I took out a book on magic, and I took out a book on chemistry. And you would think that there's nothing here that links the two. But in fact, there is. Because chemistry can look like magic if you don't understand it. And of course, a magician never wants to reveal his tricks, but in chemistry, we want to reveal the explanation. We want to take away the magic. And that is really how it all started for me. But let's get going with some of the science here. Because it was a dark and stormy night, and it really was. And someone knocked on my door, and I opened the door, and standing there was a salesman. And he was all wet, and he asked if he could come in. So I said, sure, come on in. He says, can we go and sit down in your kitchen? Sure. So we go sit down in the kitchen, and he looks over at my water tap, and he looks at me, and he says, sir, is this what you drink? So I said, yes, this is what we drink. Not only that, we even give it to the dog, and there seems to be no problem with this. And then he looks at me, and he says, do you know that there are chemicals in that water? Well, I thought that maybe it was a bit too soon to tell him that, boy, did you knock on the wrong door, because I wanted to see where this was going. So I said, what do you mean? Do you mean the H2O? He says, no, that's not what I mean. I mean the invisible chemicals that are present in your water. So I said, if they're invisible, how do you know that they're there? He says, I'm going to show you. So he opens his briefcase, and he takes out this device. And he puts these two electrodes into the water. He connects it to the battery. And within a few seconds, the water starts to turn sort of yellow. And after a minute, it becomes this grungy color. Now, at this point, I already knew what was happening here. I recognized this as iron hydroxide, or rust. And I knew where it was coming from. It wasn't coming from the water, it was coming from the electrode. But I still wanted to see where this was heading. So he then reaches into his bag and he takes out a water filter. And he passes my tap water through the filter, and he collects a glass. And then he proceeds and he puts the electrodes back into that glass, and nothing happens. So the message was clear. These dirty chemicals were in the water, but once you use the filter, they disappear. That was the message. So at this point, I thought it was time for a little chemistry lesson. So I took a little bit of salt, and I put it in the water. I said, now put your electrodes back in there, which he did. And of course, the same thing happened. Why? Because for water to conduct electricity, you have to have some ions dissolved in it. Pure water doesn't conduct electricity. My tap water, of course, has some calcium and some magnesium, so it does conduct electricity, and it allowed the iron electrode to put iron into solution. Now, the filter is actually a pretty good filter, so it's removed the ions from the water, and therefore there was no conduction of electricity, so it didn't happen. But you put a little bit of salt in there, and of course it conducts again. Now, by this time, he was a little confused. So I thought I needed something a bit more dramatic. So I picked up that glass and I drank it, because I knew I was only giving myself an iron supplement. His face turned the color of that solution. He couldn't believe that someone would do something so crazy as to drink that. And then I tried to explain to him, do you remember ever in school doing an experiment called electrolysis, where you pass a current through water and oxygen forms at one end, hydrogen at the other, but if one of those electrodes happens to be iron, then the oxygen reacts with the iron and you get this rust. I'm not sure he understood this. And then I confused him further, because I bought one of the filters. Because I had been looking for a good filter, not for any of this silly reason, but because it does take out any bad taste in the water. So this poor man was all confused, and he walks out of my house, and I'm looking through the window, and he goes to his car, he opens the trunk of the car, he leans against the trunk, and he lights up a cigarette. This man, who was so worried about the tiny amounts of chemicals in the water, didn't recognize that when he was smoking that cigarette, he was inhaling all of these toxic substances. Well, this is sort of an interesting story, and I think the salesman really believed what he was saying, because he really didn't understand the chemistry. However, this is a different story, because these foot baths are sold for around $600, and they're supposed to cure all kinds of disease, as you can see. You put your feet into this, plug it in, and within about 30 seconds, that water turns dark. And the idea is that the toxins are coming out of your body. And it's very impressive, because you see it happening. But this is exactly the same trick that I just told you. The reason that you get the color forming is because on your foot you have salt. You're always releasing some salt. So you get the electric current flowing through there. The reason that, of course, I was able to understand what was happening was because of my background in chemistry. But unfortunately, I've also found during the years of teaching students and speaking to the public that people are generally scared of chemistry. They think that chemists are these crazy people locked up in a laboratory somewhere, and they just think about what new toxins they can put into the environment. They think that we're different from other people. And this is the battle that we constantly fight. They read books about all the toxins in our life. And you can buy chemistry sets these days, believe it or not, with no chemicals required. Just boggles the mind of, where we have come since Galileo's time, and now we're into this kind of silliness. People think that chemistry is the work of the devil. Of course, I don't share that. I think that chemistry should be in the limelight, because everything in the world revolves around chemistry. All the drugs we use, the food that we eat, cosmetics that we use, the water we drink, everything has some chemical context. But of course, not everyone knows that. And unfortunately, these days, with the growth of the social media, as you well know, there's so much misinformation out there, especially about chemistry. And in North America, we have a lot of these so-called influencers. And this lady looks very pretty and very engaging. She has no science background, but she has millions of followers on social media. And her big claim is that, she's going to try to protect us against chemicals, and if you can't pronounce it, you should not be eating it. Well, I think if I offered her some beta-fructofuranosol alpha-D-glucopyranoside, I think she would run in the other direction. I don't think she could pronounce it. Probably the translator can't pronounce it either. But in any case, this is just sugar. That's the chemical word for sugar. So once you start to understand chemistry, you can get away from a lot of the panic. And this is what we do through my office at McGill. We're university-based, and our mandate really is to separate sense from nonsense. And as you know, there's a lot of nonsense out there. Until I came to Italy, I didn't know that spaghetti actually grows on trees. And I heard that this year you had a very good harvest in spaghetti. It was very good yield. Of course, you're probably familiar with this story because this was on a popular program on the BBC called Panorama. And people believed it. They actually believed that spaghetti grows on trees. So you never know what people can believe. You can sell them dehydrated water, and they will buy it. Well, to tell you the truth, that's a joke item. But this is not. Aerobic oxygen. You can go into a health food store and buy aerobic oxygen. I don't know where you would buy anaerobic oxygen, but here you buy the aerobic oxygen. And they tell you that we are starved of oxygen because of all the pollutants we're putting into the air, and there's not enough oxygen. So you have to put a few drops of this into your glass of water and drink it every day to boost your level of oxygen. This, of course, is total nonsense. The oxygen content of the atmosphere is the same as it has been for millennia. And what they have in here is a tiny amount of potassium chlorate, which could release a trivial amount of oxygen. But of course, we don't breathe through our stomach. We breathe through our nose and our mouth. So this is just crazy. But what is interesting is that after they talk about this and try to sell you that, then they point you to the next aisle where you can buy some antioxidants. And they don't see the irony of this situation. So there's just nonsense absolutely everywhere. People don't know what gluten is. They just know that it's something that's scary, and they'll try to go and get a gluten-free haircut. You can sell just about anything to the public. We're in the danger of being overrun by what we call quackery or pseudoscience. And I'm a big fan of Sherlock Holmes. And the reason is that there's a classic line in Sherlock Holmes' story. It's a capital mistake to theorize before one has data. Insensibly, one begins to twist facts to suit theories instead of theories to suit facts. In science, of course, we look for the facts, and we base everything on that. Now, you'll notice that there are ducks in the background in this picture, and that's because I do collect the ducks. And I've been asked many times, why do I do that? Because these ducks quack. And in English, of course, the term quackery we use to talk about anything that is not factual, anything that's pseudoscience. And because I talk a lot about quackery, at one time, someone gave me a gift of one duck. And that's how it all started. Then I saw another one somewhere. I thought, maybe he needs a partner, so I bought that. And now it's become what some people say is an obsession, is I collect these ducks because I like to be surrounded by them in my office because it reminds me of the importance of fighting quackery, because it's absolutely everywhere. When COVID came, What did they do? Of course, it unleashed all kinds of quackery. In India, they started to promote homeopathy as a solution to COVID. Now, I'm sure some of you are familiar with homeopathy. It is the most absurd of all of the alternative therapies, where you take a substance and you dilute it. You take 1 drop, add 99 drops of water, take 1 drop, add 99 drops of water, etc. Now, because today we can calculate concentrations and we know molecules, we know that after you've done this 12 times, there's not a single molecule in there. It's nothing. All you have is water. And then you take some of that water and you put it on a sugar pill and you have the homeopathic remedy. It cannot possibly do anything because there's nothing there. Well, I shouldn't say there's nothing there. It has a good dose of placebo in there. If you believe that it can do something, then it can. The power of the mind is really very, very powerful. But then there are some ultra-ridiculous things in homeopathy, like homeopathic X-ray. How you dilute an X-ray is really beyond me, but what they will tell you is that this relieves itching or skin rash aggravated at night and in bed. But I guess if it's during the day and you're not in bed, then it doesn't work. But of course it doesn't work anyway. This is total nonsense. And yet there are millions and millions of people around the world who do believe in homeopathy. There's a lot of scientific illiteracy out there, unfortunately. And this is what we try to fight. I'll give you some examples. I got this in my mail, this advertisement in the mail, and it was for underwear. And this was supposed to be especially good underwear because it allows moisture to pass through. Let's take a look at the picture here. H2O, also known as sweat, is attracted to thermoscans like picnic. And if you look at the diagram, the graphic artist thinks that the water molecule, first of all, has a bond between the 2 hydrogens, but never mind that. Also believes that this is miraculous underwear because it separates the oxygen from the hydrogen. As you can see, as the water molecule passes through the underwear, it becomes oxygen and hydrogen. This underwear supposedly produces electrolysis, the same kind of nonsense that I talked about before. If this were so, all we would have to do to solve the energy crisis, because we're looking for new things all the time, is just wear this underwear, collect the hydrogen, and solve the energy crisis. Of course, this is absolute nonsense. And I've been dealing with this kind of nonsense for a very long time. I have a radio show in Montreal, which actually you can listen to because now it's on the internet as well. And it started 43 years ago, but the only reason you know that is because you see the telephone in the picture. And anyway, I don't remember the very first question that I was asked back then. I was young and eager, and I was kind of nervous doing this. And I thought I heard the caller ask this rather incredible question. This is something else the translator will have a bit of trouble with. But anyway, I was kind of surprised. I didn't know, what this was all about. But then it turned out that the caller realized that he had been speaking very quickly because he had also been nervous, and he left out a very important word, which was golf. He was asking about the golf balls. And as I discovered from the conversation, golfers sometimes have the habit of kissing the ball before putting it down, but he also knew that golf courses contain pesticides. And therefore, he was worried that when he picked up the golf ball and kissed it, he would pollute himself with the pesticides. I mean, not a totally unreasonable question. So, of course, I got into a discussion with him, and I explained that only the dose makes the poison, which I have said, thousands of times over the years. And I explained that, the amount of pesticide that could be transferred to his lips was very, very unlikely to be enough to cause any kind of harm. And I also told him that there were better things to go around kissing than golf balls. I don't know how much of that message he took home. But this is the kind of stuff that we deal with. More recently, I was asked, is tripolyphosphate a chemical? Well, you see, as soon as I hear that question, I know what they're really asking. What they're really asking, is this bad? Is it toxic? Because that's what chemicals are. They do bad things. Well, it turns out that this lady who had called had come across tripolyphosphate, this nasty chemical in her mind, in a cleaning agent. And it's actually a pretty good cleaning agent. And you look on the label, and there's the sodium tripolyphosphate. So I explained to her that despite the fact that this may be difficult to pronounce, it actually does some good things. It ties up the minerals in the water, which would interfere with the action of the detergent. So this really makes for a better product. And I think I was able to convince her, because if you expect to find chemicals somewhere, it's in cleaning agents. People are okay with that. She calls me 2 weeks later. I recognized her voice, but it was full of panic, because she had again encountered the same chemical, but this time it was on a different product. It was on a food label. And this is a substance that's very popular in North America called Kraft Dinner. If you have never heard of it, good. This should strike fear into every Italian heart. Okay? But anyway, in North America, it's a very popular item. So she tells me, you know, I give my son Kraft Dinner every day, which apparently was not a problem. She says, what is a cleaning agent doing in there? So I said, look, sodium tripolyphosphate is actually a multi-talented chemical. Here it's performing another purpose. It allows the starch in the macaroni to absorb water more quickly, so you can cook it more quickly, so that when your son screams for his daily allotment of Kraft Dinner, you can produce it very quickly. And I said, look, there's nothing to worry about here. The amount of phosphate in there is much less than what you would eat in a piece of meat, which naturally has phosphate occurring in it. I'm not sure I was able to convince her. I think she had an idea that the company, to boost sales, had actually put a cleaning agent in there because they knew that eating their product was a messy business, and that this was cleaning the kid from the inside out. This is the kind of thing that we fight. Because they read books like this. The Dictionary of Food Additives by Ruth Winter. This lady has no business writing such a book. Now, how do I dare say that? For several reasons. I think the chance that she's in this room is very small. And we're not in the US, where it's a very litigious society where they're ready to sue. So I think I'm quite safe to say that she has no business writing such a book, but I can prove it. Because if my phosphate-fearing friend looked up in this book, trisodium phosphate, would find cuticle softener, bubble bath, bath salt. Yeah, that's what you find, cleaning agents. And then looking further down, she would also see incendiary bullets and tracer bullets. So now she would worry not only about her son being cleaned from the inside out, but him bursting into flame and disappearing without a trace. She makes the most fundamental error, confusing phosphate with the element phosphorus. Phosphorus is nasty. Phosphorus does burn. It is toxic. But when you combine it with oxygen to make phosphate, that's a completely different story. You don't have to worry about that. But books like this create a great deal of panic. And they create a great deal of confusion. And it's understandable. Because of the scientific illiteracy, there's a lot of confusion. One day we're told butter is killing us. You should switch to margarine. Then we find out it's margarine that's killing us. And it goes on like this. We're told, eat fish. Fish are good. They contain the omega-3 fats. When you give omega-3 fats to pregnant women, they give birth to babies with higher IQs. And then we find out that there's PCBs and mercury in the fish. So you say, whoa. And there's problems like this everywhere. Back to my tap water. Well, we chlorinate the water to make it safe, but that produces compounds like trihalomethanes, like chloroform. Those are carcinogens. So you say, okay, I can't drink that. I better drink the spring water. But then you find out that that spring water is stored in these large containers, which are made of polycarbonate, and that's leaching bisphenol A into your water. And bisphenol A is a highly toxic substance, so say we better get rid of all of those kind of water containers. So let's just drink from the single serving water bottles that you see everywhere. And then you find out that that plastic, which is a polyester, is made using a catalyst, antimony chloride. And if you remember your chemistry, that's in the same family in the periodic table as arsenic. So being in the same family means that it has similar properties. So say, all right, well, we can't have that either. So there's worries everywhere. However, the reason for that is that people do not pay attention to measurements. They do not pay attention to numbers. Numbers are the currency of science. We're always measuring things, right? That's the theme of this conference. We're always measuring. We are looking for numbers. So when we take a look at these water bottles that I just mentioned and the fact that they contain some antimony, the question you have to ask is not whether it's there, but how much of it is there. Well, we know how much because we can measure it. It's about 3 parts per billion. That still doesn't tell you very much because you don't know how much is toxic. We have to have a number to compare it with. Well, this also we have because we have done studies on antimony. We know its toxicity, and we know that the acceptable daily intake is at 6 parts per billion, which means that if every drop of water you drink in your life contains 6 parts per billion of antimony, you're okay. That's still safe. But this is only half that, so this is not an issue. So we always have to look at numbers. And of course, Paracelsus, 500 years ago, laid the cornerstone of toxicology when he said, only the dose makes the poison, right? Numbers matter. You know that if you have a headache, you can take aspirin. How much? If you take a tablet of aspirin and you lick it, your headache will not go away. If you take 2 tablets, your headache will go away. If you take the whole bottle of tablets, you will go away. So toxicity is based upon numbers. So let me play a little game for you and show you how easy it is to mislead people. I think most of us would agree that apples are pretty healthy to eat. Well, what are you really tasting when you bite into that apple? This is just a partial list. These are the chemicals of which the apple is made. These are not additives, they're not pesticide residues. That's what's in the apple. So for example, you have acetone. That's the same stuff that you have in your nail polish remover. And it says on there, do not drink. Good advice, right? Because acetone can be toxic. Also, you have formaldehyde. Well, this is the stuff that is used to embalm people. This is what morticians use, to preserve a body. And formaldehyde is a toxic substance. It's in fact a carcinogen. And if that rubs you the wrong way, there's some rubbing alcohol, 2-propanol, also present in that apple. So I could tell you this story and say, all of these toxins are there in the apple. And that when you bite into that apple actually is biting into you. But this would be total nonsense because the amount of acetone and formaldehyde and propanol in there are trivial, and our kidneys and our liver handle it very easily. So it's very safe to give apples to our kids. We don't have to worry about there being nail polish remover in the apple. But it would be possible to scare someone with leaving out the numbers. And that's what these alarmists on social media do. The fact is that we live in a world that, of course, is made of chemicals. No matter where you look, everything is made of chemicals. A lot of them. Chemical abstract lists about 200 million known chemicals. Of course, most of those, more than 99%, are naturally occurring, like the ones in the apple. But there are a lot of chemicals. A lunch can contain hundreds of different compounds. And if you take a look at our breath, it contains hundreds of compounds, so does our saliva. We are a bag of chemicals. That's what the human body is. And when you sip that cup of coffee, which you do every day, several times, I don't know how you get away with those little cups, but you sip from them, and anyway, you know what you're sipping? Over 100 different compounds, over 1,000 different compounds. All kinds of compounds, including some that are known carcinogens. In animals, in high dose, they can cause cancer, but we know that coffee does not cause cancer. This we can say for certainty. There are enough people all over the world drinking enough coffee. We would have seen it epidemiologically if there was a connection. There isn't, despite the fact that it does contain some carcinogens. Again, this underlines the idea that the dose makes the poison. So we're taking in chemicals, we are releasing chemicals. Our urine is full of all kinds of chemicals, including the bisphenol A that I talked about before, because epoxy resins are used in the lining of cans of food. And so much of food at some time has been in can somewhere. I mean, even that tomato sauce, sometime, was delivered in a can. So yes, we have bisphenol A in our urine. The question is, does it matter? Again, it depends on the amounts. They're trivial amounts. Now, of course, what we don't know is whether or not those trivial amounts over 20, 30, 40 years, if they may make a difference. We just don't know. Because, unfortunately, in science, we often have to say, I don't know. Certainty is very, very elusive. We talk in terms of probabilities. We talk in terms of making educated guesses. That's really what we do. And these days, we are at the mercy of my colleagues, the analytical chemists. Because of the equipment they have these days, the gas chromatograph, the mass spectrometers, we can find things down to parts per trillion. You know what that is? The width of a credit card relative to the distance between the Earth and the Moon. We can find that. And this can create a great deal of panic. This is not finding a single needle in a haystack. This is finding a single needle in a world full of haystacks. So if you know that there's one needle somewhere in one haystack in the world, are you going to worry about the good old-fashioned roll in the hay? No, because the benefits outweigh the detriments. So you have to know what risks are worth worrying about and which are not. Life is full of risks. Everything we do is full of risk. You don't always think about it consciously, but you came here today and it was risky, especially out here with the bicycles going crazy. Yeah, it's risky business, but you decided that it was worthwhile coming here today, and I hope it was. So we, of course, try to control risks. That's what we try to do. But it isn't always possible. We cannot control every risk. You can be out for a casual walk, and it can be a very risky business. Oh, don't worry, we're nice people, we faked it, they're fine. But they're not the innocent little creatures that you think they are. There is a risk in absolutely everything that we do, and we have to know how to evaluate the risk. when people take a risk knowingly, they don't worry about it so much. What they worry about are risks that they can't control. Worry about risks in the food, preservatives or whatever, because that's not in their control. But in other aspects of life, they're willing to take big chances. It's a very interesting, mental thing that people worry about things that they can't control, but if they can control it, they're willing to take a risk. It's always a question of weighing the risk against the benefit. And this is not always an easy thing to do. I'll give you an example. This is kind of stuff is constantly in the news. People are worried about Teflon, which is the lining on pots and pans, which makes it easy to take out the food. So where did this study come from? It was actually an Italian study. And what these researchers did was they looked at diverse areas in Italy where there was exposure to these compounds we call perfluoroalkyl substances, PFASs, because in some places there were factories that were producing some of these and it gets into the groundwater. So they wanted to see what the difference was between the areas where there was PFAS in the groundwater and where there wasn't, and they did a very interesting measurement. They measured the length of the penis of teenage boys. I guess you can get teenage boys to volunteer for anything. So they were able to do that. They measured it. But with every measurement, there is a possible error, right? So when they measured this, it came out to 9.7 plus or minus, about 1.6. And then they measured it in the control group, where there was no exposure to PFAS, and look what they found. Well, obviously, these numbers are not statistically different. If you look at the plus minus, they overlap, right? So I don't think it has any sort of effect on this particular part of the anatomy. So although this story was used to scare people from using the Teflon pots and pans, because they were worried about what it might do to that rather important organ of their body. But when you look at the measurement, there's no need to worry, because there really was no difference. So it's always interesting to look below the surface, to see what the science really is. And so it is the case with pizza. And there is an issue here, because when you heat any kind of carbohydrate mixed with an amino acid called asparagine, we get a chemical reaction, and that can produce a compound called acrylamide. And that indeed is a cancer-causing substance. It's a carcinogen, so we do worry about it. And the chemistry is well known. Whenever you have glucose, and anytime you have starch, like of course you have in pasta and in pizza, and you have the amino acid asparagine, which is a very common amino acid, and you have heat, you produce acrylamide. And acrylamide is a known carcinogen. So it is something to take a look at, to study. And it has been studied. And of course, again, we bring in the dose makes the poison. The amount of acrylamide that is present in bread or rolls or in pizza is way, way below than the amount that causes cancer in test animal. And that's how we determine if something is a carcinogen, by what it does to a test animal. Humans are totally different species, right? But anyway, we know that in this case, the amount of acrylamide is minute. But nevertheless, Italian scientists have made a step forward here. And what they found is that if you introduce the enzyme asparaginase into the flour before you make the pizza, you get rid of the asparagine, and therefore you don't form any acrylamide. It's an interesting scientific finding. I don't think it has any practical significance, because there's so little acrylamide in there that it's not a concern. But anyway, I was very happy when I had the pizza here last night, which I have to tell you really was the best pizza I've ever had. And I've been to Italy before. I've had elsewhere. This last night really was the best pizza that I've had. And very little acrylamide. As you can see, there may be a little bit on the side where it's burned, but it was okay. So I don't think you have to worry about the acrylamide. But I want to leave you with some interesting points to think about, how to evaluate science when you come across all of these sort of scare stories. Well, the first thing to realize is that the presence of a chemical does not equal the presence of risk. Just because you find out that there's bisphenol A somewhere or there's acrylamide somewhere, it doesn't mean that there's a risk. You have to ask the question, how much, and how that amount relates to what we know is toxic. There are some other questions to take into account. As you know, these days, the word natural sells. You put natural on a package and it sells, because people think that if something is natural, it's better than anything that's made in the lab. I can tell you that in my many years of being in this business, that's probably the biggest myth that I have to fight. Nature can be very dangerous. Bacteria, viruses, fungi, these are all natural. Scorpions are natural. Mosquito, which is the most dangerous animal in the world because it causes malaria, is of course natural. And synthetic chemicals are the ones that we make in the lab, but these are also the drugs that save people's lives. So there's no such equation. You cannot determine if a substance is dangerous or not by its history. It doesn't matter if it was made by Mother Nature in a bush or by a chemist in a lab. The question is, have we studied it? It's the molecular structure that matters, and from there we go on. And children are not small adults. This is also an important point to remember, because something that may be totally safe in an adult can be unsafe in a child, because when your nervous system is developing, it's a very different story. So we have to very carefully look at toxicology when it comes to children. But we also have to realize that so much of our toxicological studies are done on animals. And the human is not a giant rat, with some exceptions. But you cannot automatically extrapolate from what we see in a mouse or a rat to a human. Unfortunately, we cannot do experiments in humans. So we have to take the animal data, but we have to take it with a grain of salt. There are substances that are toxic in animals and not in humans, and vice versa. And even in closely related species, for example, dioxin, which is an industrial byproduct, is one of the most toxic substances in the world. It's never produced on purpose, right? It's always a byproduct. It's extremely toxic when you give it to guinea pigs, but hamsters can frolic in it. And these are very closely related species. Another example would be chocolate. Imagine that chocolate didn't exist. I know it's a horrific thought, but imagine. And if it was a new product just come on the market, and you decided, I don't want to test it on rats, I want to test it to something that's closer to us, like a dog. Well, we'd never have chocolate, because chocolate is toxic to dogs. We, of course, eat it, and this is one case where even children can eat it. We're not worried about toxicity here. But don't give it to your dog, right? Because the compound theobromine in there is toxic to dogs, but not to humans. Another important point to understand is that science can never prove that there is not a risk associated with something. You cannot prove a negative. It's always possible that there's someone somewhere in the world who will react to something. Because even when you're testing drugs and you're testing, for toxicity, efficacy, etc., and you have maybe in your best studies 3,000 people. Well, it may look totally safe there because you're not going to pick up a side effect that occurs 0.1% of the time, but when millions of people are taking it, you're going to pick it up. So we can never have 100% safety. You can never be totally sure about something. And there are always opposing views in science, no matter what. Whether it's climate change, whether it's vaccination, there are always opposing views. But the important thing to realize is that just because you have two views doesn't mean that they have equal validity. Sure, you have people, even scientists, some scientists, who say that climate change isn't real. But these are 3% of all the scientists. So just because you have opposing opinions doesn't mean that they have equal weight. And you can find a study to show almost anything you want to show, because every single day, every minute, 5 new studies are published. That's the average. So there are millions of studies on everything. Many of them are good, many are bad, most are mediocre. You have to know how to interpret these studies. So one thing that we really must not do is cherry pick. That is to have a pet idea and to find the one scientific paper that is in line with what you're thinking. When we want to make recommendations to the public, we have to shake that cherry tree. We have to collect all of the cherries, and you mash them together, and then you taste it. And then you find out, what the recommendation should be. And the role of anecdote is not data. Just because your neighbor has, some opinion and tells you this little story about how they may have been cured of their cold by taking echinacea, and someone else tells you that as well, it doesn't mean that this is science. Okay, what we really need is proper studies, proper research, not anecdotes. And it's not possible to predict everything that happens. Science is very complicated. The human body is very complicated. We cannot predict everything. Who could have predicted back in the 1930s when we were using, in refrigerators, we were using ammonia and sulfur dioxide as the gas, the refrigerant gas. It was a big problem because you had a leak in your kitchen, you'd inhale, ammonia, highly toxic. So we replaced it with freons, the chlorofluorocarbons, because it was much safer. Who could have predicted back in the 1940s that 50 years in the future we would find freon in the upper atmosphere destroying the ozone layer? How could you even think of something like that? Today, of course, we're much better at predicting because we have a mountain of evidence on so many things. But no matter what, you cannot predict all consequences. But one of the biggest problems is the lack of realization that correlation is not the same as causation. There's more ice cream sold in the summer, and there's more sunburn in the summer. It doesn't mean that ice cream causes sunburn, right? That's a very strong correlation, but it's not causation. And in this case, it absolutely looks ridiculous. And you all understand that this is ridiculous, right? And why there is this correlation. But if someone tells you that there's a correlation between the use of glyphosate, which is a herbicide that is used mostly on genetic modified crops, and you see an increase in autism, and they show you a graph like that, it can look very convincing. But that doesn't mean that it's causative, because I can also show you a graph about the rise in autism and the rise in the sales of organic foods, right? It's a very strong correlation, but there's no causation. So this is, of course, a very important concept to understand. So finally, with all the worries that we have about chemistry in our life, the fact is that we know a great deal about toxicity, we know a lot of chemical reaction, and what we are doing these days is pursuing what we call green chemistry. where we want to make sure that the yields of our chemical reactions are as high as possible. We get as few side products as possible. We use the safest chemicals because we learn through experience. We're much more knowledgeable today than we ever were. So this is not a case of me cheerleading for chemistry. That's not the point. The point is that chemicals should not be feared, they should not be worshipped, they should be understood. And it is education that liberates us from all the fears that a lot of people have. And I suspect that this may bring up some questions, but I also have to tell you that science cannot answer every question. We try to answer a lot of things, but we also have to understand that the world is very complex and there isn't an answer to everything. Anyway, this is what we do through my office. You can always contact me. I'm happy to answer any questions by email. We have a newsletter, a weekly newsletter that we put out for free, of course, and you can sign up for that. And if you have any questions, certainly I'd be happy to answer them, but won't leave you with one last idea, because I started with a rope trick. I want to leave you with one as well. And I hope that with what I've said here today, I've been able to unravel some of the mysteries of chemistry for you. Thank you.